In our session, so we'll start with Bertrand Duplantier from SLE Saclay, who will maybe tell us a story about Greg, or maybe just tell us about SLE.
Okay, thank you, Mr. Chairman. Yes, I will tell you a story about Greg. Yes. Well, no, not really. But we'll see. So anyway, this is a talk. I would like to thank the organizers. I'm very happy to be here during this conference in the honor of Greg. So I'm going to speak about SLE quantum multifractality, which will be the quantum version in Liouville quantum gravity of the usual multifractality you know in SLE. And it's based on joint work going on actually with Gaëtan Borot and Jason Miller. So just before I do that, I would like to remind you, if you could shut the lights, but that's okay. I guess you can see. Sorry? Yes, that's right. So I would like just to mention briefly the life of and the passing out of Sam Edwards, who was a well-known polymer physicist, a member of Caius and Gonville College, where you were all enjoying the dinner yesterday. Van Lin mentioned him yesterday. I've known him well. He was, among, I would say here, 4 physicists who were really, who somehow developed the theory of polymers. And the first one was Paul Flory, who got the Nobel Prize in Chemistry in '74. De Gennes, yeah, okay, go ahead. You can do it, okay, if you wish. And De Gennes, who got the Nobel Prize, French physicist, who got the Nobel Prize in Physics in '91. Edwards, and who just passed away, and Descloiseaux, who was at Saclay, who is retired now, who was actually my advisor. And so they set up the theory of polymers as we know it now, somehow for applications, but many of you are mathematicians, young mathematicians, and you probably almost never heard of these people. Maybe the French people know about De Gennes. But, and so Sam Edwards actually wrote a book, which is a famous book about the dynamics of polymers. And actually, when De Gennes was nominated for the Nobel Prize, actually, I know that letters were circulated where people were asking whether Sam Edwards should also receive the Nobel Prize. He did not, but he was really... So, and actually, I wanted to mention something, before I go really to the heart of the matter today, I would like to mention something which many of you do not probably never saw, which is what is called the Edwards model, which dates back of 50 years ago, exactly. And I wrote it in the naive physicist way, meaning an energy, an Hamiltonian, which is the first part. So RFS is a trajectory of your path, which will be ultimately a self-running walk or self-running path. And so this is a physicist way. So this is just the square of just the energy of this path, the Dirichlet energy. And then there is an interaction term which measures how much intersection the path has with itself. And there is a coefficient B. So this is a naive way, the physics way, to write actually the Wiener measure for the Brown motion. So the Wiener measure is really the exponential of minus this first term. And then you had the interaction term. It's not a model which is solvable, meaning you can't calculate all partition functions because of this term here. And it has a long history. I'm mentioning it because somehow there is a contact with SLE, ultimately. And also there will be a contact with Greg's work. And there was so here actually you will see I've chosen dates in such a way that are every 10 years, because somehow, and it did fit, actually, it did fit very well. So the first major progress was the fact that actually that model can be written as a phi-4 field theory, where the field phi has n components. But then at the end of the day, you have to compute correlation functions of this field theory in the n equals 0 limit. So it's famous n equals 0 limit De Gennes, which was part of this Nobel Prize. And that, cast the whole polymer theory in the framework of renormalization theory of field theory, a la Wilson. And Wilson also got the Nobel Prize in '82 for his work on renormalization applied to statistical mechanics. So that was really a major thing. But actually later, 10 years later, Descloiseaux understood that you could actually, if you were really interested in polymers and not field theory, especially not this odd limit, you could actually work with the Edwards model and do perturbation theory, meaning expanding in terms of in the powers of B, and actually predict physical properties if you were, astute enough to actually do a direct renormalization of what is called renormalization of the model. So, and actually it's a beautiful model because actually S is really the length of your path, so the time if you want in terms of Brownian motion. B is the interaction parameter. You are in D dimensions. Of course that term is relevant only when you are in less than 4 dimensions. So actually it is cast in this term in terms of this interaction parameter, which is really the only parameter you have in your model. If you calculate dimensionless quantities, everything will be expressed in terms of this interaction parameter. That's it. And actually you see that as long as D is less than 4, that parameter scales to infinity when you scale your path to infinity. So it means very long chain will have very strong interaction, meaning that the second term actually is going to lead the statistics of your path. It's a beautiful model because it has very few parameters, and if you are able to extract the laws of this, the physical, say partition functions of this model, you are going to have access somehow in the limit where S goes to infinity or equivalently B goes to infinity, you are going to have access to actually the statistics of self-folding walks in the scaling limit. Of course, in 2 dimensions, it's not a very good model because you would extract properties of SLE, but it's very hard to do this way. So here I just mentioned the fact that you can generalize this model to, in the physicist sense, meaning you can look at polarized membranes, meaning the internal parameter space, which was the path, the abscissa along the path, S, becomes D-dimensional. You would like to have 2 dimensions for having a real membrane, but actually you can define a model properly in terms of a dimension which is between 0 and 2. And it's a very nice theory. You can reduce the whole renormalization theory to all orders. And I think not one probabilist ever looked at this model, but it really has a lot of nice properties. You have only one interaction diagram to each order. All the Feynman diagrams are resummed at once at each order. And you have only one, it's like string theory. And you can work in this kind of abstract, non-integer dimensional spaces. There are ways to do that, to do geometry in those spaces properly, in terms of distances. And you can really define a nice model, and ultimately I'm sure some probabilists will look at it. Anyway, in 2D, you all know that there is a famous conjecture by Lawler, Schramm, and Werner in 2002, that the self-folding walk scaling limit should be SLE H3, of course. Of course, I'm sorry?
It's a prediction.
Well, I made the prediction, but you had made the conjecture. So anyway, so I'm just joking with it. But I mean, if you know Coulomb gas, of course, you know the way we used to do conformal field theory. That was what you had. Anyway, so I should say we made, because a lot of physicists, Ninois, all of these people, Ninois in particular. So, but anyway, so it's still an open conjecture, and if anybody of you could go and see Greg and say, hey, I have an idea, let's work together on this, I'm sure Greg will be very happy, for a birthday present. One first step in this direction actually was done by, of course, by Nienhuis, actually, because really, of course, many of you don't know Nienhuis, a great guy. He's a Dutch guy, great in many senses. And he, once he went to the top of the Mont Blanc, but he had forgotten his glasses. So when he was about to take the telepheric, to go at 3,000 meters high, before the ascension, he just realized he had no glasses. He was in the team as a physicist, decided to go nevertheless. Which of course he came back almost blind, but still he recovered from it. So anyway, so this is Nienhuis. So he made kind of groundbreaking work in terms of the theory of self-folding walks in 2D using the Coulomb gas in '82. And of course, we all know now that Demidil-Copin and Smirnov, and Smirnov, Hugo, actually shown recently that the self-folding connective constant on the Onekang lattice actually is given by this formula, which was actually predicted by Nienhuis. So anyway, it means, so in a way, I'm back to SLE here, of course. So as self-folding walks, polymers, are really at the heart of SLE. They are just one very good model for SLE. And of course, there is this kind of striking open question. I think I'm spending too much time on this, maybe. I just wanted to mention this, that actually the Edwards model is also valid for a famous problem in probability theory, which is the intersections of Brownian paths. So in that case, you just take 2 Wiener measures, well, just again, written in the naive physicist way. Actually, you can compute with these things, of course. This is why physicists like this. They don't write W's of inner measure, just compute with this kind of quadratic terms. And then you put an interaction term, which is just the measuring the local time of intersection, the local intersection time of your true Brownian path. And you take the exponential of -h, and you look at the scaling limit, if you can, in terms when b goes to infinity, or s goes to infinity. And if you do that, so you are able to somehow predict some things. But I just want to mention here, I will go very fast, a number of works, of course, about this problem. So, Greg really started the game here in 4 dimensions in '82. And then, of course, there were some work by Eisenman, Felder and Fröhlich. All you can remark that they are all in communications in mathematical physics, at least at that time. Then there is also the usual suspects, Le Gall, who we see here. Actually, I also worked on this using actually that Edwards model. Greg was doing something else. He was doing real probability theory. So I use renormalization theory, non-rigorous, but gives you exactly the same prediction laws as Greg's. And then of course there is a work of Bird. There is this here appeared, this famous 5-4 or 5-8 you mentioned yesterday. Birdie and Lawler, of course, the works that were mentioned yesterday in the talks at the dinner. The 2 main works here about the existence and of the intersection exponents. And of course, Yuval Perez also appears. And of course, there are other works. I just made a kind of selection of all of this. And you see that Greg was really here at the top of the tower. And by the way, well, here is, this is a picture. Greg mentioned yesterday there was this number 5-4. Well, actually, you could wonder where this 5-4 appeared. Actually, just on the bottle of wine here. This is where he found it, and this is really the root of the. So of course, you also recognize the usual suspects. This is Michael Eisenman, who offered that bottle, and of course, Oded is here at the table. So. Let me go to my problem. So anyway, I go back to the subject was SLE quantum multifractality. Okay. So somehow the project started here with this question that I don't remember. I don't know if you remember the talk by Gaëtan Borot, for people who were here in the last workshop, say in April. He had calculated with Boutier the large deviation spectrum for the number of loops surrounding a given vertex on a large random planar map. So they had this nice universal deviation function for CLEs in quantum gravity, say, and he had the formula, and he said, I've been trying to compare this formula with the formula obtained by Miller, Wilson, and Watson, yes, Sam Watson. So Jason Miller, Sam Watson, and David Wilson. And he said, I have been trying, and it's not clear how to do that. So this was actually the motivation for the work. But I'm going to start with something which is a bit simpler. I will show you how you do that later at the end of the talk. But I will just give you a simpler problem where you can do it quicker somehow, and which is about the harmonic measure. So a brief recollection of the harmonic measure multifractal properties in the plane first. So I will try to I have too many transparencies. I was fearing to have too few, but actually just the opposite, unfortunately. So I might have to skip some. So anyway, you have here the setup, say a random curve, actually here a Brownian path, just to fix the ideas. You look at the potential, the Dirichlet potential theory of this, condition 1, 0, and of course, you know very well that, so this is Laplace equation with those boundary conditions, and you know that this potential can be recast as an harmonic measure problem. So the probability that a Brownian path, another one, the blue one here, it's 1 before 0 when started at p. Okay, so you have this harmonic measure, and the multifractality properties somehow in a naive way can be recast. Described in this way. So you have your path. Of course, the harmonic measure is going to charge only the boundary of your path, and here that's again the Brownian motion. Say just for as an example, and you look at points along the boundary where the harmonic measure in a small ball of radius r scales locally like r to the alpha. This is a naive way because actually you have to take a slightly larger and smaller exponents and try to take the limit when you zoom to a given alpha. And then anyway you collect all your points along the frontier which are of type alpha, and you measure the Hausdorff, you try to define the function f of alpha, which is the Hausdorff dimension of your point of type alpha. And here I've put some names of the people who actually somehow established this kind of formalism. Of course, it's much bigger. There is a huge community working on this now, in general. And just for people who are, so what is the meaning of this alpha? Well, you can see it, this local exponent, you can see it in a way like, so if you go back to the potential description of the harmonic measure, if you look at a wedge, if you look at the potential in this wedge, it's going to scale like r to the alpha, where alpha is pi over theta, where theta is the opening angle. So it means that because theta is between 0 and 2 pi typically in the plane, you will have alpha between 1/2 and plus infinity, meaning that an alpha equal 1/2 corresponds to 2 pi, so it means really a needle, because you have opened your wedge to a needle. So the lower values of alpha cannot be smaller than 1/2, and of course they can go up to infinity, and when alpha goes to infinity, that means theta goes to 0. It means you are entering fjords. So I just mentioned this naive picture because we are going to have the equivalent of this kind of things in quantum gravity later, and the things will be different. So well, about the spectrum, last time, in January, I spoke about the integral mean spectrum. If you calculate an integral mean spectrum, you can derive the f of alpha by a Legendre transform, a type of Legendre transform from the beta spectrum. But just to tell the story, just to give you the present day answers, well, for the bulk of SLE, the f of alpha is given by such a formula, which, alpha is here and kappa is here, and that's it, of course. And that's a universal formula. And of course, there was an announcement, like, say, in the first conference here in this program by Green, Miller, and Son, that actually they could prove this formula almost surely. So in their case, of course, the f of alpha will be a dimension of a set. So actually, this f of alpha will stop when f of alpha reaches 0. When you do it in expectation, like in physics, like we did before, like Belayev and Smirnov, and some work I did before too, you actually, your f of alpha just go underneath. We are going to see a picture in a minute. And I want to mention also the tip spectrum, which explores the harmonic measure properties near the tip of the SLE, which was actually calculated first in physics, predicted in physics by Hastings in 2002, and actually proved to be valid almost surely by Frederick Johansson Wiklund and Greg Lawler in 2009. That was the first example here of spectrum almost surely in the SLE framework. And of course, there is also this big progress here for the bulk. So this is the kind of formula you have. For people who are not versed in multifractality, they look this way. So I just took the SLE at third. So it looks this way. Again, I took the expected spectrum. So it means here I just did not cut when you reach 0. So we go underneath, happily so, in physics. And the spectrum, just is asymptotic to, well, physicists like to think in terms of continuations of dimensions, limits n equals 0. They are not bothered by this kind of things. It's being glasses. You take replicas, and then you take 0 replicas, and you still get something. So this kind of thing. So of course we go to negative dimensions happily. So so anyway, the top of the f of alpha, of course, is always the Hausdorff dimension of your path, which is the 4/3 for the SLE at third. So again, this is the kind of formula you have with b, which b here is 25/12. This b characterizes the SLE. Remember, b was here given by this formula, and you get this kind of hyperbola. And of course, the almost sure spectrum, you get it when you just cut the f of alpha along the horizontal axis. So, so where do I want to go with this? Actually, it's too bad I don't have 2 hours, but actually, I want to deconstruct this spectrum first, because I want to look at, ultimately I want to look at what would be the analog of this spectrum in quantum gravity on a random map, say, and in Uri quantum gravity. But just to do it, I'm going to prepare the the ground, but just deconstructing this f of alpha, I tell you exactly how you could calculate this formula if you were a physicist. So, well, so usually what the standard multifractal form is relates f of alpha to a symmetric Legendre transform, tau of n, which is given by this kind of formulae. So you know you have f of alpha, you do the Legendre transform, and you have n given by the derivative, alpha given by the other derivative. And actually, if you do that, n is the order of the what is called the multifractal moment of the harmonic measure. Then there is a way to define a scaling dimension. So if you're in conformal field theory, that will be a conformal weight of your CFT. So x of n, so it just tailors the way you should tailor it. So xn is canonically defined in terms of tau of n as, 2xn minus 2 equal tau of n. So then, for instance, if you have the Hausdorff dimension, the maximum is when df of the alpha equals 0, so n equals 0. That corresponds to tau, the dimension being f of alpha corresponds to this, which is minus tau of 0 by this, and which is 2 minus 2x 0. So you have this tau of n, and as I said, you have the x of n. So what are those x of n? Well, they are given by this kind of definition of the moments of the harmonic measure. You take the harmonic measure in small balls, you make a covering of your boundary for a certain domain, and you sum over this covering here, and your moment is going to scale like a certain power of your small ball here, and maybe divided by the power of the radius at which you started your Brown motions. So anyway, and here you have this actually tau of n, or xn. So if you deconstruct this f of alpha I showed before, well, they are going to be given by this kind of general formulae, which are of the KPZ type. So you don't necessarily know what KPZ is here yet, but typically x of n is going to be given by a certain function u, depending on kappa, of an argument which itself is given in terms of the inverse of u, depending on n. Remember, there are only two parameters here, n, the number of Brown motions, and kappa, the SLE parameter. Okay? And actually, this kind of formula actually is really inspired from the Lawler and Werner 98 work on Brown motions, so where they just devise cascade relations. And actually, when Wendlin, sent me an email one night, on Friday night I was at Saclay, telling me, well, I'm speaking tomorrow Saturday at IHP. Maybe this is about Brown motion intersections, packets. Maybe you would like to see it. So I went there, and he had all of these fantastic predictions with cascade relations for Brown motions, which became later properties of the restriction for measures. And of course, so he had this structure, but then if he was using the conjecture for the intersection exponents of a certain number of Brown motions, not packets, but split Brown motions, then you would have a lot of square roots everywhere. And of course, if you knew quantum gravity, it was just full of quantum gravity, even so you asked in the plane. So clearly there was something happening in quantum gravity, of which all of this was an image. So anyway, this is typically this kind of formula. And of course, it's also in the spirit of the welding of quantum wedges, like started by Scott Sheffield in 2010, and which you find also in this later paper. So anyway, I'm not going to go into the details. I just want to say that there is such a formula, which we'll use later when we go to the quantum version of the multifractality. And so this is when I say welding of quantum wedges, you have this kind of quantum surfaces. You weld them together. They are welded along SLEs, generalization of Scott's work, actually, initial work. And then, if you glue together the boundary of your complex plane, then you are going to get an extra SLE. So this is for multiple SLEs, but of course there will be a kind of corresponding picture with the harmonic measure. Anyway, so this u of kappa, so you have a single function here, which actually will be the KPZ relation, and which will be seen later, and this u of kappa is given by this formula, so it's just a quadratic form in terms of delta. Delta is just a variable here, and x is the result. And kappa, of course, is here. But of course, if you do quantum gravity, there is a gamma parameter in quantum gravity, and thanks to Scott, we know that actually gamma square should be kappa, where kappa is actually less than 4. because gamma square is always here less or equal to 2. So, and then of course, if you have an SLE kappa prime, where kappa prime is greater than 4, the gamma square will be just a dual. There is an inverse to this quadratic formula, which is given by this formula. So I'm just telling you exactly what kind of formula you have. I'm not, explaining more here. I just want to mention something, which is a work in progress with Scott and Fredrik Johansson Wiklund. And so if you look at the tip multifractal exponents, there are also xn's for the tips, which are x hat. They're given by a similar formula. So the same KPZ formula, except that the argument won't be the inverse of u, it will be the inverse of another function, which is a modified KPZ. So here you had 4, and for the tip you just put 8, and everything will just follow. So this is just a little technical part. So this is all the preparation for the quantum version. So I'm sorry, because somehow I may be taking too much time on the classical case. There was something which we developed with Ilya Binder a while ago too, which is the winding and harmonic measure spectrum. So you look at locally the possibility that your SLE path makes a lot of a really long spiral. So you look at the winding angle when you approach a given point on the SLE, and that can be really wild. And actually, what you try to describe, you're trying to describe the points where locally you would have a double logarithmic spiral. So the SLE is just winding like a logarithmic spiral, meaning that the winding angle should be some lambda times log of r. The r is the distance to the center of your ball. So this would be the winding angle. W is just the point, the center of the ball, and r is the radius of your ball, right? And that is going to scale like lambda log of r. And then you define a mixed multifractal spectrum, meaning you look at the set of points on the frontier of your path, of your SLE, where the harmonic measure is going to scale like r to the alpha, and the winding angle is going to scale like lambda log of r. Okay? And then you define f of alpha lambda as the dimension of the subset f of alpha lambda. Well, again, here you can define moments, right, which are defined like before, like you sum over a covering of the frontier with, you look at the nth moment of the harmonic measure, you take the exponential of p times the winding angle. This is, of course, a kind of double Lejeune transform on alpha. So anyway, you take these two variables, they will scale like r, like little r to some power, and you call this exponent x of np. And of course, no surprise, later, the f of alpha lambda we had here will be the double Lejeune transform of this 2x minus np. Well, being a physicist, I could not resist, and I use transmutation tools, to somehow describe this winding Brown packet of Brown motions and SLE. The black thing is in SLE. The packet is here. You can transmute them into kind of non-integer number of, so you still have your black frontier SLE, and then you have packets of SLEs. If you do that, you're able to calculate x of np in terms of x of np. And actually, it's given by this nice formula, which is x of np is x of n shifted by a p square term only, so kind of Gaussian in logarithmic terms, and then normalized by x of n. And b, of course, is a parameter which depends on kappa. So this kind of formulae are very simple. Of course, this one is kind of a bit intricate. But anyways, I'm going to use them later in quantum gravity. And of course, if you have this kind of relationship, which I ask you to admit here, this is not the subject of my talk. This is work done a while ago with Ilya Binder. Well, you do a double Lejeune transform, okay, of this tau, 2x minus 2, and you get your f, in terms of the taus. Okay, so, and if you apply it to this kind of multifractal spectrum we saw for the harmonic measure, remember it had this form with b, the single parameter depending on kappa, so we had this, it was giving this nice hyperbole. If you do that, apply this, so this from this formula, this kind of structure, so you see n and p as here, and b is the parameter here. From that kind of structure, when you do the double Lejeune transform, you get actually this kind of scaling law, that f of alpha lambda is given in terms of f itself, the single f, the harmonic measure 1, provided you divide alpha by this kind of quantity. And if you apply this scaling law to Z form, you get something which is very simple, which is the same as before, except that here in the denominator, this term has been shifted by lambda square. Anyway, here are the names of people who contributed, over the years to this analysis, either in physics or in mathematics. Needless to say, in physics it's not rigorous, but the aim is to calculate, to have still the right formula. So, so where do we stand now? We would like to somehow have the equivalent formula if you do everything in quantum gravity. What does it mean? It means I would like to know what happens if I take, say, if you are pre-scaling, you take a huge planar map, you let random walk diffuse or hop on your random map, and you take balls. Well, balls, not exactly balls, that's the point. If you take balls using the metric, right, which you don't know always how to, that could be the discrete metric, the graph metric, you are going to end up depending on the construction of this metric in the scaling limit, which is not assured yet, so except for the Brown map, of course. So this is not what you do, because actually this multifractal spectra, they are really measure problems. So what you can do simply, instead of looking at the metric balls, you can look at what we call quantum balls with Scott in our paper a while ago, where you just look at so on the graph you would just take balls which would depend, the measure of the ball with just the number of sides of your little domain. And you will look at the harmonic measure, which is the probability that you random walk, if you're on a discrete setting, just, hit that ball before hitting the rest of the SLE, right? Which would be an ON loop, for instance, or a FK cluster if you're in the discrete setting, for instance. So clearly there will be the correspondence, but of course clearly there will be a scaling limit, and the scaling limit you hope to get by using the continuum model. But since we need only the measure here, it will be enough to use the Liouville measure, right? And you use just Liouville quantum gravity defined as a random measure. So I would like to know exactly how to define this and how to calculate things once I know of course, to solve the problem on discrete setting is not necessarily trivial. But if you have the continuum setup, you might be able to actually derive one setting, the quantum one from the classical one, the planar one. So, well, the GFF, so just a quick reminder, of course I'm going to go very fast. Just the weight is Gibbs weight. The H will be this distribution with Gaussian weight, and such that the direct linear product in the domain D with some of two test functions will be just a covariance of the projection of F with the inner product, direct linear product, the covariance of HF1 subgradient, HF2 subgradient. So that's one way to define anyway, you all know the Gaussian free field. This is a nice picture done by Jason Miller. And I have a movie done by Namkyu Kang, who's going to speak just right after me. This is just a sampling of the Gaussian free field with coefficients which are Brown motion. So this is why the variance is increasing with time. But it gives you somehow, if you were rescaling in your own mind, you would just give you a sampling of different values of GFF. Of course, there is a rigorization. This is why the spikes do not go up to infinity. Yeah. So I just show this because that was a nice movie. If you take the Liouville measure, you will try to define a random measure which will be the exponential of gamma h times the Lebesgue measure. And of course, so I have another movie done by Namkyu, but it doesn't work so well. So maybe we'll go. Let's see. I had some problems this morning with this. Okay. So you see, just increase gamma, and for a given sample, and you see the occurrence of these spikes due to the exponential gamma h, where h is big. And of course, it's not spectacular. Usually, we insist on the spikes, but actually, there are also places where h is very negative. So places where you have very few mass, very few area, which are the little, pieces here. And of course, here the Gaussian free field was taken to have zero boundary conditions, meaning that on the circle you have value 1 for exponential gamma h. I'm not sure the next will work. Yeah. There was, sorry, I don't know. I did not realize there was a technical problem this morning. Anyway, here we are. So this is the same thing but where gamma is going to be much higher. And then num_q would be just a rescaling that in such a way that this picture would stay in the screen. So I'm sorry, because a lot of people have seen it many times, I guess. And then you go at the end of the day, when gamma reaches 2, your scenery is dominated by huge spikes. But of course, it's very fractal underneath, and you don't see it. Okay, let me go back to full screen. I can jump. Oops, not what I wanted. Okay, so you have to define your measure, and so you define a mu gamma, which is a limit of exponential gamma h sub epsilon of z times a small regulator epsilon to z to gamma square over 2 dz. So you see this is an h sub epsilon of z is the average GFF average on a circle of radius epsilon. And so you show that, so you multiply this by this quantity by this regulator here, because actually this exponential blows up when epsilon goes to 0 typically, and this is a Lebesgue measure, and you show that this actually converge weakly for gamma less than 2 to random measure, which you write naively this way, even though it's not absolutely continuous with respect to Lebesgue. And actually that somehow there were some hints of this in an old work by Höckron, and of course Kahn did it without us knowing it in the setup of multiplicative chaos, and but this is the definition I'm going to use later. And of course, if you want to, I'm not going to use it here, but if you wanted to look at boundary multifractality, you would have to use a quantum boundary measure, which is defined the same way with different power here. And here, this h hat is just the average of h of free boundary GFF on semicircles centered at on the boundary of h, on the real line. Anyway, so I'm going to, so we know this exists, but somehow keep this in mind because it's going to come back when I look at quantum balls later. I'm going to somehow use an approximation of the measure which will look very similar to this, to the pre-limit, or the pre-epsilon going to 0 limit. If you are at gamma equal 2, you have a problem because all of these limits for gamma equal to 2 or greater vanish. So you have to define, a derivative martingale on this way, or a renormalized one, which is the same as before, except that you enhance your measure by this square root of log factor. If you do that, you do get a measure which is non-atomic, and so it converges weakly to a random measure. And of course, if you go above 2, well, that's finished. You have a duality, you have spikes, you have to do something else, so I'm not going to mention here today. So, KPZ relation, very fast, because I gave you the formula, but many people know about KPZ. Maybe some people are not very familiar with it. So if they stay in the plane, and so it was invented by Knizhnik, Polakov, Zalmodnikov. You have your random fractal, preferred one, say that's a self-holding rock here, for Greg, or it could be a bound motion. And then you look at some particular properties of your path, say in the plane. So say the probability that it intersects, for instance, as an example, small ball of radius epsilon will scale like epsilon to the 2x. The Hausdorff dimension will be then 2 minus 2x. And in that case, and then you look at the same problem, same intersection problem in terms of the quantum balls you would define with your random measure, the one which you just defined. So this is a drawing made by Jason Miller here, and you have seen this kind of picture of Liouville quantum gravity, and then you look at the intersection properties of your random path, which is sampled independently of the quantum gravity measure, of the Gaussian free field measure. And of course, then in terms of these little quantum balls or little quantum squares here, the intersection probability will scale like the power of the measure of the ball to some new exponents, capital delta. If you are at the boundary, you will have tildes. And then your KPZ prediction is that actually the x and the deltas are related by this famous formula, which is quadratic, where gamma is just the parameter you put in to define your random measure, the Liouville quantum gravity. Okay, that was. And of course, now this is a theorem in probability theory, and actually there are many derivations, including latest ones using the e-kernel, where Nathanael and actually Christophe Garban and Nathanael Beristiki were part of. So this is just of course, many of you know about this. And now I want to go, before I go to the the question of the multifractality in quantum gravity, I want to define, to have a good feeling of what is a quantum ball. Okay, so I go back to this expression. Remember, the measure was defined as a limit of this kind of expression. But if you want to have an approximation of your measure, well, you can take as a definition of the quantum ball measure just the exponential of your circle average, then pi epsilon square, which is just a Lebesgue measure of your small disk, and then your regulator. And actually, you can show that this is actually and when epsilon goes to 0, will be actually a good approximation of the real measure, where you would take the limit first, and then integrate this measure on small ball. Right? So I'm going to use this naive description. And actually, in the work with Scott a while ago, we showed that given z, h of z is standard Brownian motion bt in terms of t, which is minus log of epsilon, plus a deterministic term, which comes from this pi, so the fact that you rooted your measure, which is minus gamma log of epsilon, which is gamma t. So pay attention to this formula, because it's going to come back in the multifractal approach. So, and delta, of course, will come back also. So if you believe that, you rewrite this in terms of bt and gamma t, and you have a nice expression that delta is the exponential of some Brownian motion with drift. And the term here, A, is not any term, is 2 minus gamma square over 2. And gamma being less than 2, this A is positive. And if you take the log, which will be important for multifractal measures, minus log of delta is just AT minus gamma BT. Well, so Brownian motion with drift. So, well, you wonder, so you have a stochastic object. It means if you give yourself a circle of radius epsilon, the amount of quantum mass which is there is going to be given by this kind of expression. So you can draw it. So, for instance, you give yourself a Euclidean ball, B sub epsilon of z, right? And you say that the stochastic area of this ball, the quantum area of this ball, equals delta at the stopping time, which is the first time where your AT minus BT reaches the level A, where A is minus log of delta, right? Because remember, you had this. You give yourself a value of delta, which is the value of A, which is here. If delta is small, of course, A will be large. And then you have AT, which is A, remember, is positive because of gamma less than 2. So A is positive, AT here. And then you add this Brownian motion. And when you reach, the sum of the two reaches A, you stop, and this is your TA, right? Now, you can look at the distribution of the given a T or given an A, what is the distribution of the epsilon you need, or the epsilon A, the TA, right? What is the distribution of this? And actually, if you do that, you can compute it, of course. And you have something which I will use later, which somehow will be actually a key ingredient in this naive approach to define quantum multifractality. You will have a certain distribution, which is the probability density that your stopping time belongs to the interval t plus dt. So I recall that t is minus log of epsilon, so it's really t is in the classical world, in the plane, right? And delta here, namely when you take logs, capital A, right, is in the quantum world. So you fix yourself a quantum ball of measure delta, and you look at what is the distribution of the Euclidean radius epsilon which you have for this delta, right? But you write it in terms of these logarithmic coordinates, meaning you define, again, A like minus log of delta, and again, T as minus log of epsilon. So if you do that, you have this nice formula, and you see A is given, and T is the quantity which is normalized probability density. So it has this typical form. So you have T here, T here. A is the famous A, which depends only on gamma, and that's it. Okay, all the kappa dependence or gamma dependence is here. Okay, so we are equipped with this, and now we can look at the initial question of trying to define a quantum multifractality, okay, for our SLEs. So somehow I cooked up the right formulas for you here without too many explanations. So we had an f of alpha. You remember all of these multifractal formulas f of alpha I defined before. in the plane. So typically, now you can recast it in this way. If you look at the probabilities that you have a point of type alpha in a ball of radius r, r being, such that, well, actually, this is r before it was, we had epsilon, but that's the same thing. And t is minus log of r. That probability will scale like exponential minus t minus 2 minus 2 alpha. This is just a recast of the definition of the f of alpha, right? And it means the harmonic measure here is h is scaling like r to the alpha, meaning minus log of h is scaling like alpha t, if you have this definition. Little r is the same as epsilon before, right? And if you are in the quantum case, what you have to do is the following. You have to give yourself A and alpha g, I will explain in a minute why, and multiply your probability, which is given by this large deviation, by P of t, which is the probability density that we observe for a given delta, we observe a given classical radius. Okay, so it's a convolution of this type. And if you calculate things right, meaning if you do a saddle point approximation, because actually, of course, I did not say it, but when a goes to infinity, the distribution is more and more peaked, as you can see here. The blue one corresponds to 200 for a is much more peaked than the lower ones. So you will have, so P of alpha will be given by this large deviation for t large, and because you have r going to 0 here, and you are going to fix not r, but you are going to fix a. And so if you fix a, which is the quantum equivalent of t, right? You fix a, you fix alpha g, which will be given in such a way that the harmonic measure is either of the type h equal r to the alpha, or in the quantum setting, the harmonic measure will be given by delta to the alpha g. So the alpha g will be the quantum counterpart of the alpha, right? The quantum alpha, if you want. And if you do that, so because the harmonic measure is the same, that's the same, in both settings, because you use your Euclidean setting underneath, this alpha t equal alpha g. So you have this ratio, meaning that if you condition on a and alpha g, it means the alpha t will be integrated over, and alpha will be also moving. So you have to calculate these things with this moving alpha here, and if you do that, by the way, I should say that somehow this f of alpha, so if you do that, you are going to get this kind of form, and this f of g alpha g is in some way the quantum multifractal spectrum, meaning the dimension of a set of points, where the measure on the delta quantum ball scales as delta alpha g. It's not really a dimension, Hausdorff dimension. It's in the sense that if you really wanted to have the Hausdorff dimension, you would have to multiply by the overall Hausdorff dimension of your random surface, which we don't know. But if you up to this factor, you have a kind of definition, proper definition of the Hausdorff measure, right, of the measure for the quantum setting. So if you do that, so remember, so now you have this general formalism. You have this P of t, PA of t here, right, which we have here, which is kind of precursor of KPZ. But remember, I'm going to do something that you should never do. I'm going to go backwards very fast. Remember, we had this f of alpha was given by Legendre transform of a spectrum, and the spectrum tau of n was itself, this tau of n or x of n itself given in terms of KPZ formula. And if you do this, you are going to find in all generality for this type of setup, you are going to find the following, that your f of alpha, fg of alpha, now I just use a running alpha here, the fg, the quantum one, is given in terms of a symmetric quantum Legendre transform, tau g of n, which is given so by the same formula as before, so except that you have sub-labels g, and where actually the point is that tau g itself here is given by delta of n minus 1. Before you had 2xn minus 2. Here you are in quantum setting, you have delta minus 1. You lose a factor 2. That's always the case when you do this KPZ business. But the point is that this delta of n is the inverse image by KPZ of the x of n. Right? So this is the result you find from the general setup. Provided, of course, you know that x of n is a scaling dimension, because you can't apply KPZ to any quantity. So anyway, but remember, maybe you will remember if I go very fast, so close your eyes. I do what I should never do, of course, but still I should have put the formula. Remember that we had this nice formula that x outside itself was the image by KPZ, by the KPZ formula of a certain argument. So if you take the inverse, that's just the argument here. So somehow all the work is done already for you because of this cascade structure. Let me go forwards now. And okay, so it means this, you have just here, this delta of n is given by this argument we saw in the previous formula. So I skip the details. You calculate, and you find this nice formula. You find that the SLE quantum harmonic spectrum is given in terms of the standard spectrum, tau and f, by this shift. So this is just due to the precise formula for the harmonic measure. So this says the planar ones, f and tau, are given in terms of the quantum ones by this one. So n is invariant, that's a number of paths. So it doesn't change in quantum gravity. What changes is alpha and tau. And if you just eliminate n, you are going to find a closed form formula for f of alpha, g, which is given by this. So it's again an hyperbola, right? 1 over alpha, alpha g. It depends on kappa, of course. It's universal. But the interesting thing that you have here to take kappa as the smallest of kappa and 16 over kappa prime. So it means you have to take, if you have an SLE kappa where kappa is greater than 4, you take the dual value, and this is the one you plug here. You have to be a bit careful here. The other formula was symmetrical in the kappa 16 of kappa. This one is not. But you have to take the mean here for kappa. But there is something striking if you look at it, that alpha g now, before there was a singularity at alpha g, alpha equal 1/2, which was this Berling theorem that you cannot have alpha for the harmonic measure less than 1/2. In quantum gravity, you go up to 0. And the reason is that you have this alpha can be smaller because you have domains where you have very, very small mass. So the harmonic measure, so the r to the, so you have very small delta, so delta to the alpha must be big enough in such a way that you have some harmonic measure, meaning that since delta is so small, your alpha should be also, the alpha g should be also small. And this you see it here, you see that you have a shift, right? Because it's clear here that you start at alpha 1/2 for this one, here you start at 0. Yes?
The SLE is independent of the quantum gravity.
Yes, but this is not, yes, it is independent, but the, no. Well, it's, you know, that's a famous thing that that's a work, you know, of Scott. It is that here I take, of course, the value of the gamma, which fits with the, which is fixed in terms of kappa. I did not take a gamma independent of kappa. I took gamma square equal kappa, or the mean of kappa and 16 of kappa, right? So it, and you know, at the end of the day, you know what happens, that from the quantum gravity structure point of view, the SLE is independent of the Gaussian free field. That's exactly the point. And the welding and so on. So yeah, thank you for the question. But indeed, this is just KPZ for that value of gamma. Yeah, like in the old days in physics. Because in physics, at the old days, they were always taking the gamma corresponding to the university class of the model. They were not mixing both. Anyway, so they have nice properties like all of these, independently of kappa, they all saturate at 1/2. This is what you expect. Because these dimensions, if you do them in quantum gravity, if you like the physicists you used to do, you all know that for the dilute, the kappa less than 4 model, you all know that the dimension you have is 1/2, the delta. Well, Scott knows what I'm talking about, but anyway, not everybody knows. But anyway, you remember, for the other, for the classical one, the planar one, all of these F alpha, they saturate at the Hausdorff dimension of your path. Here's different quantum gravity, they all saturate, all go through 1/2 as a maximum. And you remember in the classical case, you have the Markov theorem telling you that f of 1 equal 1. Here, there is no Markov theorem, but you have this universal top value. Remember, if you really want to have the Hausdorff dimension, you have to multiply by the Hausdorff dimension of your LQG surface, which we don't know, maybe Watanabe formula. And of course, that dimension will depend on kappa or gamma. Anyway, so this was an example. I also did the quantum tip spectrum. Remember, we had another formula, thanks to the discussions with Scott and Frederick. So you have another type of formula, again universal, again, you know, of the hyperbolic type. Again, the max is 1/2 when kappa is less than 4. You have two formulae depending on whether kappa is greater than 4 or smaller. So I write kappa prime when it is greater than 4. And well, whatever, they are explicit formula. And what else? Oh yes, so I'm sorry I forced you to look at all of this winding story because I wanted to see what happens in quantum gravity. So sorry to have imposed this to you. And the formula is, the best I could do was a parametric one. I doubt you can find something else, but because there's fifth order equation at the end, so could not solve it. So, but it's essentially you have it in terms of parameter. You remember we had this complicated. So I'm doing, totally. I should never do with your students. So where was it? Yeah, later. Well, here we are. Remember we had this thing, a bit complicated. So and the Xn itself was a Kapisi formula. So from that one you have to go to the quantum thing. Well, you do it, and you have this formula, which is my best bet for today, which is this one. So it's f of alpha, f g of alpha g lambda g is given in terms of an extra parameter lambda, which is -1 and 1. Lambda g is given in terms of lambda and alpha g, and f itself is given in terms of lambda and alpha g. And if you look at that, it has very nice properties. And I'm sure the formula is correct because there are a lot of properties you should have. And in particular, you can fix lambda and look at the maximum in terms of alpha g. Then it depends on lambda g, in this case explicitly, whatever. So you probably don't want to know all of these details. Just saying that these formula are now on the market. And to conclude, I would like to go back to the original problem, the motivation for this study, which was the nesting in CLEs. So you had this nice result by Miller, Watson, and Wilson of last year, where they look at the number of CLEs loops of a conformal loop ensemble, where kappa is between 8/3 and 8, which surround a ball of radius epsilon, and they call this set the set of point z, where the number of loops scales like the log of 1 over epsilon times a certain nu. Okay, nu is going to be a parameter, and you look at the dimension, Hausdorff dimension. They can show almost surely that the Hausdorff dimension is given by a certain function gamma sub kappa of nu, and this gamma is given by a certain formula, which is the value at 1 over nu of a lambda star, which is itself the Legendre transform of a function capital lambda or little lambda. So you have a Legendre transform here. This is in terms of x, and x is 1 over nu. And this is for nu positive, but when nu goes to 0, this formula converges to a certain value, which is this one. And the formula capital lambda of little lambda is given by this log. So you saw that a few months ago, and so which is explicit thing. Of course, if you try to calculate the Legendre transform, you are going to have other explicit formula, which I skip. And the result by okay. And the result by Borot and Boutier of this year, not published yet, which was explained by Borot in this talk, that was the nesting of ON loops on a random planar map. So you look at the probability that you have n loops. So you take a large volume V of your random planar map. They really did it by an explicit calculation with random planar maps. So it's really something which is honest as a mathematical calculation. You look at the probability that in this volume V you have a number of loops which is A times D. D is a running parameter, the red D here, times log of V, and that is given by a large deviation function, which is V to the minus theta of D. And the theta of D was given by this formula. It is for an ON model, so it depends on n, an ON loop model. It depends on D explicitly, and that's it. And of course, the coefficient A here was a bit special. It could be, if it is an ON dilute model, meaning in terms of SLE kappa less than 4, then it would be a fixed value. And for the dense case, which corresponds to the kappa greater than 4, you will have an extra formula where B is a parameter which parameterizes the ON model. And in passing, I also mentioned that actually this is the way it got it. This theta of D is actually also a Legendre transform of another function which is given here. And the question was, are these two results related, and how? So of course the answer is yes, they are, by Liouville quantum. So they are, in principle, in the continuum limit, And this is what you have here, because you look at large deviations. In the continuum limit, they are going to be related by LQ, by Liouville quantum gravity. But it's not totally obvious to see how, because here you have a problem of loops nesting a point. You don't have operators in terms of conformal field theory. It's not obviously KPZ working here, because you don't have scaling dimensions. So, and still you believe that indeed there should be a relationship. So of course, so you have to transform your parameters. So not going to do it here in details, but B here, which labels the ON model, actually corresponds to a certain value of kappa via this formula. And of course, when I will do Liouville quantum gravity, I'm going to use a parameter gamma, which will be given by, as usual, by the mean of square root of kappa or 4 over kappa. Because kappa here can be over, of course, can be over 4, as we saw already in the work of Miller, Watson, and Wilson. And well, if you do, so you do large quantum deviation, so you again take t equal minus log of epsilon. A, well here I've put an extra gamma for the having the right definition, so don't look at the details. So essentially that's minus the log of the quantum ball mass. And the number of loops is in the discrete setting was this one. In the quantum setting, I will define a D which is given in terms of this log of delta. So before we had V, the volume of the random map. Now I'm going to look at small quantum balls, so I use a delta. And so again, the number of loops is conserved in both settings. And so it gives you a kind of conservation law. And you just use here the information from the paper by Jason, Sam, and David. So you use the fact that your probability for given nu, which you had here. Sorry about the complexity of the formula, but you had this dimension given in terms of gamma here. So it means the probability that you had a point Z of type nu was given because of this formula in terms of this kind of power, which you can rewrite this way. You do as before, you condition on the number of loops being fixed, the quantum area being fixed, and A and D using this formula. So it means nu will change with T. And you take a convolution and you do a saddle point approximation. And if you are lucky, you are going to find something which scales like minus A times some large deviation function depending on D, the D you introduce here. And so theta D should be the quantum large deviation function for loop number around delta quantum ball scaling as, so the loop number scaling like D log of 1 over delta up to factor. Anyway, so P of nu we know it is of this form here, right? And of course P of theta, PA of T we know it was given by the form we had here. And of course you could be tempted to inject all the expressions and calculate. That's what I did first, and it took me some time. But finally, actually, you have a nice structure which you should calculate first and then apply. And actually, the nice structure is the following. So this is the calculation we have to do via saddle point approximation. And actually, it's done like doing thermodynamics. You know, I don't know if you remember your early days doing thermodynamics. They were all Legendre transforms. So actually, this is PA of T, the parameters. These are the classical radius, the quantum ball measure. Actually, in the work of Jason, Sam, and David, you had this gamma kappa of nu given by lambda at the saddle point, at the Legendre transform, lambda minus nu capital lambda, and the 1 over nu was given by the derivative. Well, if you go to the quantum setting, it's nice. Your large deviation function is given by delta of lambda. The second term is D, so nu is replaced by D, and the capital lambda is the same. But here you had 1 over nu, which was the derivative of capital lambda with respect to lambda. Here 1 of D is derivative of capital lambda with respect to delta of lambda. And this delta of lambda is a KPZ formula for lambda. So you see here, it's not as before. You don't have a direct access to the skin exponents, but you have a different Legendre transform where actually your lambda parameter is just replaced by the quantum one, right, by the KPZ. And if you just apply this with the formula I showed you, just match. Okay, so I think I should stop. Oh, by the way, happy birthday again, Greg.
Thank you, Bertrand. Questions?
it's a bit late. I suggest we leave the question for the break. So we start again at 11:30, and thank you again.